Our last talk of the day is by Neil Trevett. He is a VP at NVIDIA and president at Khronos. So he's the boss at Khronos. Neil has worked tirelessly with Khronos, and under his leadership, many successful standards have seen the light of the day. So it's a great accomplishment. Vulkan, OpenXR, OpenVX, NNEF now. They're all under his leadership. So we're very happy to hear from him. He's going to be talking to us about APIs for accelerating vision and inferencing, basically options and trade-offs. So please give a warm welcome to Neil Trevett.
Thank you. And thank you for staying to the bitter end. We'll try and keep this interesting. We've had a couple of Khronos-related presentations, but this one's going to be a little bit different. This is where we zoom out and look at the total industry as a whole and not just the Khronos APIs. It's interesting to see how the different API options fit together, the trends and the patterns that are emerging. Hopefully it's insightful. This is the fourth time we've actually done this kind of overview, but it changes completely every year. Things are moving really fast. So I enjoy putting these together. Hopefully it's useful for you too. So this is a sampling of the API and language ecosystem for vision and inferencing. It's just a sample. If your favorite API or library isn't there, apologies. I'm just trying to illustrate really the layering that is really becoming more and more pronounced each year. As we all strive for performance and portability, time to market, layers are appearing where each layer leverages the other. And at the top, we have the application libraries, the use cases that are most interesting in the industry right now, things like AR and inferencing. And then those layers, as you go down through, they'll be trying to use one or more of the layers underneath them to reach into the underlying hardware for efficient acceleration. So what have we got here this year? On the top, I've picked out a few use cases. There's augmented reality, which is particularly active in the mobile space. A lot of both Apple and Google are putting a lot of effort into platform-specific augmented reality libraries. Of course, there's inferencing and machine learning, both the training side, and there are dozens of training frameworks. I've just picked a couple. And for deployment on the edge, of course, inferencing engines. And there's quite a lot of, that's probably the most relevant for this audience in the embedded space. The platforms are all beginning to define their own inferencing stacks. Some of the hardware vendors like NVIDIA and others are defining proprietary inferencing engines. So there's TensorRT, CoreML from Apple, NNAPI from Android, and as Rada's just educated us, OpenVX is also a neural net inferencing engine across platform, vendor-neutral inferencing engine. And then, of course, we can't forget classic vision processing, OpenCV, and OpenVX. OpenVX is kind of unique. It is kind of the one library that you can use for both vision and inferencing, and you can combine the two. If you go down one level, we begin to talk about language-based acceleration solutions. We heard about SYCL from Andrew. Of course, there are other language-based solutions out there. C++ from C++ AMP from Microsoft, CUDA from NVIDIA. Largely C++ based. You're expressing the parallelism using the power of the C++ language. And they often map down one more level again. So again, Andrew was showing how SYCL can map down to OpenCL. CUDA would map down to GPU operations using things like PTX. So you have a layer of what I call explicit APIs, where you're not just coding everything in C++ and letting the compiler figure it out. You want to have, or you need to have, the control of you write your own kernel code separate to the host code, and you get to control everything explicitly, where it runs, how it runs. And at that level, things divide into two main types. There's the GPU APIs, and we're like in year 2 or 3 now of the new generation GPU APIs, DirectX 12 from Microsoft, Metal from Apple, and Vulkan from Khronos. And then we have the more heterogeneous APIs. OpenCL, again, is fairly unique in being a little bit more general purpose, giving you a little bit more control so you can spread your kernel code out across multiple heterogeneous processors. Then below that, I think is a layer that's really becoming more and more important as programmable solutions become more mature. In the past, if you had a programmable solution like SYCL, for example, or C++ AMP, you would target an API like OpenCL, for example. So you would be targeting OpenCL-C out of your SYCL compiler. But now, I think the intermediate representations for a much more mature compiler stack are beginning to appear. So an intermediate representation like Spear, which we'll talk about in just a second, is a representation that's been designed specifically for parallel processors. And it's been designed specifically to be a compiler target, rather than OpenCL-C, which was originally designed for someone to program to, being pressed into service as a compiler target. And of course, their HSA is another standards organization. They have something similar to Spear called HSAIL. And again, the hardware vendors typically will have their own intermediate representation that they will use in their own compiler stacks. So that's kind of the big picture. This was going to guide us for the next 20 minutes. Where should we start? Let's start with the AR libraries. So, of course, mobile phones are kind of an interesting way for people to get their first taste of augmented reality. You can hold your phone up as a window into an augmented world. And it's very interesting that both Google and Apple are investing quite heavily in some pretty sophisticated vision processing. It's very confusing. They're the wrong way around. The Apple one should be AR Core, right? It's the wrong way around. Anyway, they're both shipping. They both had multiple iterations, and the functionality is largely the same. The key thing they're doing is providing pose tracking. So they're doing SLAM-type processing, so they're getting the pose of the device in the real world. Very high quality if you've ever used either of these. And they're using motion sensors. Because they're encapsulating just a simple call to an API to get the overall pose, they can do as much black magic under the covers as they want to do. And they, of course, have access to lots of system facilities. They both now provide plane detection, both horizontal and vertical. You can have target images to recognize, and you can use as markers or anchor points. They're both measuring the ambient light and the temperature, so if you do 3D renderings in the scene, you can make it look as realistic as you can. Both now provide a link to neural net object detection, normally at the scene level. So if you're doing an AR scene, you can tell whether there's a cat or a dog or some other object that your network is trained to recognize. They both provide access to the point cloud, so you can begin to do photogrammetry type operations over these libraries. Apple are exploiting the iPhone 10 face tracking, and they can even use the face as a light probe, which is pretty cool, so you get better measurements of the ambient light. Google just launched multi-user cloud-based anchors, so you can have multi-user AR sharing anchor points and objects between multiple devices. So it's pretty cool. There are still third-party libraries that will build on top of ARKit, AR Core, if they're available. Or typically, if the underlying library is not available, they'll do their own SLAM processing, but they do the sensible thing, and they will take advantage of the system-provide libraries if they're there. A cross-platform solution that isn't here yet, but will be in the next year or two, OpenXR. Radha mentioned it briefly. It's an AR/VR standard. Version 1.0, which is hopefully will be here later this year, is focused on VR. But of course, it has the API calls for pose, for interacting with input devices. Future versions of OpenXR are intended to cover AR use cases, so the list of functionality will be kind of similar to this, and it will be a cross-platform standard. So inferencing, of course, the big topic. Let's talk about inferencing on that top row. This is a zoomed out picture from what Rada was talking about. As we all know here, there's two stages. There's training your neural network, and then it's inferencing. On the training side, it's typically done desktop or in the cloud. It's done on dedicated hardware like TPUs or GPUs. If you're using a GPU from one of the three desktop vendors, they're going to supply a neural network library, primarily very efficient convolutions, and the neural network will be using the APIs to access the GPU to get that acceleration. Increasingly, people want to mix and match their training frameworks, and this is why we're getting these exchange frameworks beginning to appear. In this space for authoring interchange, ONNX is probably the best known in the industry right now. NNEF is the other interchange format. You can use NNEF for authoring interchange, but I think ONNX has that as their primary design use case. Over on the inferencing side, again, kind of zooming out from Rada's picture, you need a inferencing runtime. We went through them before. Each of the platform has theirs. Things like TensorRT from NVIDIA and OpenVX is the open standard. They, in turn, will call down into one of the explicit APIs if they want acceleration. If you have a GPU on your platform, you can use one of the GPU APIs if you wish. If you want to use more heterogeneous acceleration, then something like OpenCL or SYCL layered on top of OpenCL can be a good way to get to your hardware. So how do you bridge the two? Again, the exchange formats are really coming into prominence because people want the flexibility to go from the training framework of their choice into the inferencing engine of their choice. This is the primary design focus for NNEF. NNEF was from the get-go was saying, okay, we're going to have a bunch of these formats and a bunch of these inferencing engines. We need to be able to pass over a highly optimized format. But of course, you can use ONNX too. I think it's going to be interesting the way these two compete in a loving way in the industry. We'll go into that in just a second. The key thing is the compilation and optimization going from your trained side to your inferencing side. And one of the most interesting projects out there, which isn't a Khronos standard, it's a project at University of Washington. It's been sponsored by Amazon, is an NVM. It sounds like an NVIDIA thing. It's not an NVIDIA thing either. It's an open source project, and I think this is a great illustration of people using compiler technology to really optimize networks as they want to bridge from the training to the inferencing hardware. And the steps here, you import a trained network description out of your training frameworks. On here, they're currently supporting ONNX or CoreML. That's the Apple proprietary standard. Then they do graph-level optimizations, and then they compile into primitive instructions, and they can do optimizations at the instruction level too. And as a last step, they emit programs that can be actually executable by the selected runtime device. And you can see they have OpenCL, CUDA, Metal. They have LLVM, which is the intermediate representation used by pretty much all of the CPU compilers out there. And they're doing more backends. They've just released a prototype WebGL. I put it in there because I found it was interesting. You can now have inferencing being compiled down to run in your web browser using WebGL GPU shaders for acceleration. They're actually getting pretty good performance. And the other interesting thing they're working on is a Spear backend. So this is the Khronos intermediate representation, and that gives them access to multiple runtimes. So I just want to take a moment to talk about Spear. We needed Spear because we wanted an intermediate representation that had native support for graphics and native support for parallel processing. We love LLVM, and as I say, LLVM is like used everywhere for CPU compilers. There's so much value in all the tools around LLVM. And we make sure that we can go backwards and forwards between SPIR-V and LLVM. But we needed SPIR-V not just for the extra native functionality of parallelism. We needed a stable specification that we can build the rest of our hardware stack around. LLVM is an open source project which has great strength, makes them super mobile, and they can evolve really fast. But if you're building a hardware stack, that can actually become a disadvantage, and you need a stable specification. So that's why we've ended up with two, and we're trying to make the two work really well together. I won't go into the details here, but SPIR-V has a lot of tools now, optimizer tools. You can take a SPIR-V program, optimize the heck out of it. There's lots of front-end compilers and lots of back-ends, including OpenCL and Vulkan. So zooming back out then to how do you bridge this gap between training and inferencing? It turns out that NVBM is a kind of a model. Everyone's kind of doing the same thing. And I've picked the 3 platform vendors that are now developing inferencing stacks for their platforms. There's Microsoft that has Windows Machine Learning, or WinML. There's Google that for Android has the Neural Network API, NNAPI, and Apple for macOS and iOS has CoreML. The same fundamental steps are happening each time. You're importing a trained neural network model. Microsoft is using ONNX. Google primarily uses TensorFlow, and Apple has their own proprietary format called CoreML. They optimize it, and then they accelerate it using a GPU API or some other API. So Microsoft have extended Direct3D. There's a DirectML layer on top that adds some of the common machine learning operations. Apple goes to Metal. And Android, they can go to DSPs, specialized processors, or GPUs. So again, everyone's kind of using different exchange models, which brings us back to where does NNEF fit within the industry ecosystem? The design goal of NNEF was to provide this bridge from training to inferencing. And we started it before ONNX, and we're now beginning to get a number of open source importers, exporters to the various frameworks. We already have TensorFlow and Caffe exporters, and we have a syntax parser and checker. So if you're creating NNAF files from your tool framework, you can check that the files you've created are correct. And we're working on bidirectional importers, exporters to TensorFlow and Caffe 2. We're working on an exporter to NNAPI for Android, and we're working on an OpenVX exporter so we can take NNEF into OpenVX, as Radha was just explaining. I think it's interesting to compare the two. Having two things can be confusing, but they're both independent. They're both kind of started under their own steam. The competition can be good, but at Khronos, we're definitely open to cooperation too. We need to figure out what the right thing to do is for the industry. So we'll see how things work out. But the differences are, ONNX is cool, and NNEF I think is cool too. As I mentioned earlier, ONNX is an open source project, which means it can be more agile, but it can be tricky for a hardware stack to be based on, just like we discovered with LLVM. Whereas NNEF is a multi-company controlled specification. And I think the key difference is NNEF has put more focus into optimizations when you deploy into an inferencing engine. So I just kind of brought out just a couple of the things that have gone into the design of NNEF. The first one is we separated the structure file from the data file. So we can describe the topology of the network separately from the set of input parameters that we want to feed into that network. The idea is that depending on what capabilities your inferencing engine have, you might want to use different accuracies and precisions in your data file. And in the structure file, we have what ONNX has, which is like a straightforward mapping of the graph of the tensors and the operation layers into a graph structure. But we also have custom compound functions. So you can do things like kernel fusion and create a compound operation that can give a lot more hints to the inferencing engine on how that network is to be optimized. The other big thing I think that NNEF has, and I'm sure ONNX will have soon, is much more flexibility over the widths of the operands. So ONNX doesn't yet have 8-bit operations, whereas NNEF from the get-go has had variable width operations. We can go all the way down to 1-bit, 2-bit, 4-bit, 8-bit, all the way up to floating point. And I won't go too much into this graph. This is the same slide that Rada had. But bringing NNEF files into OpenVX, that can be a highly optimized NNEF file. I mean, all those compiler type optimizations to optimize your neural network, they can be applied before you output the NNEF file, or your NNEF file can be optimized before it's input to OpenVX, and then your OpenVX implementation will further optimize how that network actually gets executed on a particular piece of hardware. Rada briefly mentioned OpenCL, OpenVX interop, so we're kind of clicking now down into the explicit API level. So what's happening down here in the dark depths of explicit APIs? I think this is a really important evolution for OpenVX. One of the criticisms of OpenVX has been that it's great if the kernels that you need are on the standard specification menu, but what happens if you want to do something more customized? And we've had user kernels for a while, but they would take that user kernel code and run it back on the CPU, which isn't optimal for some types of operation, obviously. You really want to have accelerated user kernels. And so now we have this buffer interchange between OpenVX and OpenCL. So you can take OpenVX data objects and copy or map them into OpenCL, and OpenVX can then drive OpenCL commands into the OpenCL runtime, so you can get accelerated end user code running within your OpenVX graph. I think that's a big step forward. The OpenCL roadmap is interesting. There's a lot of work going on. There's 3 main threads. There's the SYCL work that Andrew was just talking about. That's our route into talking to ISO, and we want to bring the parallel processing goodness into standard ISO C++. That's kind of like a long-term project, but it's definitely a worthy one. We want to provide more flexibility for people to deploy their OpenCL kernel code on more runtimes, and we're bringing that capability to Vulkan. I'll talk about that in just a second. And last but not least, we're looking to make OpenCL more flexibly deployable. So let me just talk about those briefly. So the SYCL ecosystem, again, Andrew was talking about it. I think it's actually awesome that libraries like TensorFlow written in C++ can just be straightforwardly accelerated using SYCL. The goodness of the compiler stack lets that happen with good performance, and we all want that goodness to be put into standard C++ over time. OpenCL is not available everywhere. People would like it to be. Vulkan is pretty much available everywhere on desktops, mobile, embedded systems. And we have an interesting project called CLSPV. It's an open source project. It was originally catalyzed by Google and Adobe and CoPlay. They want to run optimized OpenCL kernels on Android that has native Vulkan, but not OpenCL as a platform API. Lots of the GPU vendors ship their own OpenCL, but they use it under the covers. If you want to have a platform-supported API providing your acceleration, then Vulkan is kind of the way forward. But many people want to use the additional expressive power of OpenCL-C, or C++. You can express more than you can in the kind of the graphics shading languages. And of course, many people have invested a lot in OpenCL. It's great to give those people more deployment choices. So this open source project, CLSPV, you can go check it out. It compiles OpenCL into Vulkan SPIR-V. So again, this is the intermediate representations providing a lot more deployment flexibility. Just because you've chosen a language or an API no longer means you have to be tied down to one particular deployment runtime. So this is OpenCL over Vulkan. I think we're going to be putting quite a lot of work into making this production worthy. It's currently a prototype. OpenCL next, we're working quite hard on what the roadmap is. We want to increase OpenCL's deployability in the embedded space. Historically, OpenCL 1.0 was designed for desktop machines and HPC. 32-bit floating point was the minimum. But there are there's lots of functionality in OpenCL, and certain vertical markets, like inferencing, don't need all of that precision and all that functionality. So in the next generation, we are going to be, as well as adding new functionality, slicing and dicing the 2.2 and the 1.2 functionality, and letting people define market-specific profiles. We're going to probably call them feature sets. So for example, an inferencing feature set. And someone building a small DSP-based inferencing engine or some other hardware will be able to choose what functionality they ship. They won't be forced to ship stuff that doesn't add value to their customers just to be conformant. But we're going to try and provide feature sets so people can coalesce around agreed sets of functionality so we don't get fragmentation that's too painful. And then lastly, safety critical. Khronos has quite a bit of experience in safety critical graphics APIs. And of course, as we go into new generation applications, we need safety certifiable vision and compute. We have OpenVX safety critical. But in general, we're kind of discovering that there's not a lot of industry consensus on how we and other standards organizations should design safety critical APIs to streamline the certification process. So we've just set up the Khronos Safety Critical Advisory Forum. It's open to everybody, not just Khronos members. We're reaching out to other organizations. We're taking in the experience that we're gaining from some of our safety critical projects that are already underway. And the intention is to create a set of guidelines and ideas for the industry to use. If you're interested or experienced in safety critical, we would love you to join in. And last year, I'm going to end on a question. We still don't have an industry standard camera API. We originally had OpenKCam, but it was replaced by the Android camera APIs. But now, of course, we have embedded systems with multiple sensors, different types of sensors that we want to control in real time, way beyond the camera control that we need for mobile applications. And so we're continuing to ask the question, should Khronos do a camera control API? Again, if you have any opinions, we'd love to talk to you. And so to summarize, the whole ecosystem continues to become increasingly sophisticated. The layering of libraries and languages and runtimes is providing a lot more deployment and a acceleration flexibility. The exchange formats and the intermediate representations in particular are kind of new kids on the block that are going to play a key role. Safety critical is important, and I think we need a camera API, so let us know if we should do it. Okay, thanks very much.
Thank you, Neil, as always. 2 microphones on the aisles. If you have any questions, please line up. There's a question here.
Hello, Neil. This is Ed Royce. I'm with SocioNext. Camera control API, interesting idea. I assume this would be something that would be layered on top of the MIPI camera control standards and such. Is that the idea?
Yes. So we definitely wouldn't. There's another layering. We definitely wouldn't duplicate what MIPI is doing. MIPI primarily, as you know, are involved with the hardware connect and some status. This would be more an application level control
Right.
API. The first draft of OpenKCam was based on the Franklin Cam from Nokia and Stanford. That gives a lot of real-time control. You can set up a whole burst with different parameters, and you get a sequence of images coming in. No, we could do that, or we don't have to do that if the industry needs have changed, and we're pretty open to what the industry would require. But definitely it would build on top of and complement what MIPI is doing.
Okay, I was mentioning some people that might be interested in that.
Let's
That'd be
talk.
cool.
Yeah.
So I have a question for OpenCL.
Yeah.
For mobile embedded system. So right now, we have some customers, they want to still continue use OpenCL,
Sure.
but actually Google seems not quite support it. So, but for Vulkan, they are lacking of many features compared to OpenCL.
Right.
So what's the Khronos plan for
So
compute in mobile?
yes. So for whatever reason, no, OpenCL is not a Google-supported platform API. The many GPU vendors in mobile, including on Android, do ship OpenCL, and they use it very often in their own camera pipelines or other dedicated applications that need compute. But if you want to use a Google-supported API, now Vulkan is going to be the GPU API for the foreseeable future. Now, Vulkan does have reasonable compute. It has separate compute queues in addition to the graphics queues, so you can just ignore the graphics queues, just use the compute queues. So it's already better than OpenGL ES, and the flexibility of Vulkan is significantly better than OpenGL ES for compute-type operations. But you're right, OpenCL does have more compute capabilities than Vulkan. That's why I think the CLSPV project is interesting, and it is being sponsored by Google, as well as enabling people with existing OpenCL code to bring their kernels over onto Vulkan. It's going to be instructive, I think, on what compute functionality we should bring over from OpenCL into Vulkan and gradually improve the compute capability of the Vulkan API. The Vulkan working group is doing the right thing. They're being very pragmatic, and they're saying, we're not going to take everything you've thought of in OpenCL and then put it all in one big lump. But if you can prove to us that you need this kind of function, this kind of pointer functionality or reduced precision operands or something to meet these use cases, then the Vulkan working group will do that. And the CLSPV project is the way that we can prove those use cases need that extra functionality.
Okay, thank you very much.
Thank you very much, Neil.